All right, everyone, welcome back. Good to see at least those of you I can see. Before we start off today, just a quick warning that I'm doing this from the road, and so I'm out at a conference. So I'm in a conference center that may be a little bit loud occasionally. Hopefully the audio is fine, but please don't be afraid to jump in the chat or even unmute and ask for clarification or let me know if something's goofy, and we will do our best to accommodate. All right, so we did a super fast overview of processing in general last time, and that was obviously nowhere near enough to make anyone an expert in ceramic processing, but hopefully encourage you to think about a few pieces and aspects of the fabrication and sintering processes that you may not have before that can play a big role in the eventual electronic and electrical properties of whatever your parts are. Today, we're going to start off with essentially an ode to the multilayer ceramic capacitor because it is such a tremendous example of putting together so many different pieces of the fundamental material science and the engineering from a chemical perspective, and then a microstructure perspective, and then larger scale at actually fabricating multiple layers of a device that to be functional, and then doing this in a way that that it can actually be economical as well. And so we will go through this in more detail. I just want to start off with a little highlight of this is from Murata because they always happen to have the most fun marketing along these lines. But the same sort of thing could be applied to several different multilayer ceramic capacitor companies. Their most recent MLCC product that's shown right there, the total dimensions of that product, it's 160 microns by 80 microns for several hundred layers of a functional device that's sold for a fraction of a penny each. That's just unbelievable. So to put that in perspective, the hair on your head is probably, each strand is about 100 microns. So that's just spectacular. So what we're going to go through today is a quick overview of how the MLCCs are made. And that's all the way from the chemistry, the unit cells, all the way up to the full structure. And hopefully use that as an example so that you can think more deeply about how you might be able to scale some of your products, both physically as well as economically. All right, so to jump in, before we can appreciate MLCCs themselves, we need to do a quick refresh on capacitors in general. So again, the purpose of a capacitor is storing charge. And so that's the charge, depends upon the capacitance, the C, and the voltage that you're applying. And as we talked a couple of weeks ago, any real capacitor is going to have some non-zero amount of leakage that passes through it. And so the knobs that you are able to turn are the area, the thickness, and the relative permittivity. And we'll get into each of those independently in a little bit. So from a customer perspective, I mean, who cares if you make the world's best capacitor if nobody wants to buy it? So it really comes down to what your customers need, what they're going to be using these capacitors for. Many times these are going to be broad generalizations, of course, but generally you want as much capacitance in a small volume as possible. Keep in mind though that is for a given operating frequency or a given operating voltage. So these are always trade-offs that are associated with this. Nobody ever wants losses, whether they're in series, which would be as we talked about before, the energy dissipated getting the charge to the capacitor in the first place, or in parallel, which would be that leakage through the dielectric itself. So ideally, no losses. That's not feasible, so we want to minimize losses as much as we can. And the function, again, has to be at whatever the application demands. So that's very often the application will demand a certain voltage, and then it's up to you to provide a product, a capacitor that can function at that voltage with some amount of margin. Now, is that margin 1%? Is that margin 20%, 100%? It varies a ton. But just recognizing that you don't often have a huge amount of say in that, so you have to build everything else around a given operating voltage. Temperature is very similar. So you don't want your cell phone or your laptop or something like that to massively change its function if you walk outside on a cold day. So we need stable temperature response. Ideally, that's the highest possible capacitance, but many times the stability is far more important than whatever the maximum is at a given single temperature. And so because of this, the industry standards have come up with a variety of different classifications. The most common one for commercial application is X7R. That just says that the capacitance will not change by more than plus or minus 15% between -55 and 125 degrees C. There's a lot of push for X8R and X9R, which pushes that upper temperature bound up a little bit. There are others, X5R and others that have a different bottom end. So if you don't necessarily need to operate at -55 C, but in general, you can find depending on what your design is for the device, you can find a classification that says, all right, we're going to operate within this envelope. And then it's up to the materials engineer to design and develop and produce the capacitor that can do that. Of course, if they're not cheap, nobody's going to buy them. If not reliable, why bother? Because you don't have to keep replacing these things. The whole advantage of multi-layer ceramic capacitors is that they are cheap and reliable. You don't have to keep swapping out these integrated components all the time. And integrable, so yes, integrated components. So you need to be able to work them in with whatever the rest of your design is. So towards the end of today, we will get into a little bit about LTCC and HTCC, so low temperature co-fired ceramic and high temperature co-fired ceramic platforms. Just very briefly, as one comparison to a lot of the printed circuit board types of examples that are out there in consumer electronics. And then finally, we looked at the operating frequency. I talked about the operating voltage. The frequency is often just so baked in that it's not even spec'd. So people will, this is the class of application. This needs to be DC. This one needs to operate in the 1 kilohertz range. This one's going to be gigahertz microwave kinds of things. And those are such broad categories that are set from the beginning. And because as we talked about earlier on, in terms of the polarization mechanisms, the operating frequency really determines which flavors of polarization mechanisms you can take advantage of. These are sort of set from the very beginning, just like the voltage and the temperature stability and everything else. So you might not even find operating frequency as something that's going to be spec'd out in a spec sheet, but you can get to it by looking at things like equivalent series resistance and similar sorts of parameters that will be in there. So if we're going to be building these capacitors, one option is we would just want to absolutely maximize the total amount of area and do that with as thin a layers as possible. So one of the early technologies for taking advantage of this is you start with an extremely large surface area of some sort. So one example here is just basically foil that's been folded and then oxidized. If you take aluminum and anodize it, then you've grown an aluminum oxide layer, and that aluminum oxide layer is a dielectric. So it's a great insulator. It's not going to pass a lot of charge. So you can start with even packed powders, as shown down here, of either aluminum or tantalum. Those are the most common. There are several other varieties as well. So you can end up with a massive surface area that can give you a very large area, and you can adjust the thickness of the oxide layer that you grow on top of this by how you do the oxidation. So one example is you just put it in air and heat it up. That's an extremely crude approach, but it does work. The more sophisticated versions are to actively chemically anodize. So you could put it in an electrolyte that you use to drive the oxidation. The nice thing about electrolytic capacitors is that because of the field distribution that occurs in this process, you're going to grow a conformal layer of the oxide. So if one region happens to build up a little bit thicker, then that is going to drop a little bit less field. And so you'll end up putting more field and more current through a thinner region, which basically self-heals and self-limits that process so that you can anodize a nice continuous, very reliable thickness in your material. So great. Now we have a very thin layer, massive area. So we have a very high capacitance. The problem then becomes, if you want to operate at high frequency, the current has to get through these tortuous paths to get current into and out of the capacitor, the storage layer. And so electrolytic capacitors often end up having relatively large equivalent series resistance values. So that's what this ESR is. So because you've got a very tortuous path that led to that very large surface area, these are often limited to relatively low operating frequencies because you have to give the electrons time to make it through the conductor. Otherwise, it ends up giving you a large series resistance, which is that ESR. The other part, if we're using this voltage, it's anodization, to drive an oxidation of the metallic layer, so we're turning aluminum into aluminum oxide, for example. If we turn that voltage around and operate it in the other direction, we can drive that reaction the other way. So we can start with aluminum oxide and reduce it to metallic aluminum. This is electrolysis. This is one way that we actually separate metallic aluminum from alumina ore to create metal, the metallic species. That's probably not what you want if you're trying to use this as a capacitor. And so when you make or use these electrolytic capacitors, you're going to be limited in the voltage that you can apply in the negative polarity. So I'm defining a negative and positive in this direction by what is growing the oxide layer versus what is shrinking the oxide layer. And so that doesn't mean you can't operate them in an AC manner, but it does mean that you don't want to go overboard in the negative direction, because you can drive the reaction backwards, evolve oxygen. If you turn your dielectric layer into a metal and allow oxygen to escape in the process, guess what happens? You end up creating gas pressure, and then the capacitor blows up. That's an extreme example, but it does happen. So there was a series of capacitor failures in the late 80s, early 90s that were known as the capacitor blight. That there are many different explanations for what might have led to that, but it gave the electrolytic capacitor a bad name for a while because of, at that time, relatively low reliability compared to others. When made properly, these can work great, but you're still limited by ESR just because of the nature of the connected electrode. So I mentioned aluminum and tantalum. These are the two most common versions. There are wet and there are dry versions. So you can actually have an electrolyte that stays in the capacitor body that can increase the performance, but it can also very much limit the temperature stability, because if you've got a liquid that's going to be very responsive to temperature, you don't want to boil it. Again, you end up with a pressure buildup and explosion. So dry electrolytic capacitors are generally going to be a little bit more flexible in terms of temperature and voltage operation than the wet versions. But again, these are broad statements. So this is one possibility. If we want to compete with these relatively simple, we're just going to oxidize the layer of our electrode. We're going to get more clever with multi-layer type technologies. So if we want to make a multi-layer ceramic capacitor, we need to, within the constraints of whatever operating voltage and frequencies are, we need to maximize capacitance. So we can start by making the thickness as small as possible. So we can make very, very thin layers. There are massive practical challenges to this. So for example, you need to be able to tape cast a layer that's less than a micron thick, and you want multiple different grains within that layer for reliability concerns. I showed you the picture at the very beginning that is 80 microns thick across hundreds of layers. So now we're talking tens to a small number of hundreds of nanometers of dielectric layer each, and do that reliably. It's a big challenge. You can also increase the effective area of the capacitor by just stacking things into a multi-layer sort of buildup. So the overlapping area here between each of those electrode layers gives us the effective area where we're able to store charge. So in this region, that's where the fields will drop, and that's where the energy will be stored. So these regions at the edge are just passive. So you're not actually storing any significant amount of energy there. There's no real field dropped across those because this region is all the same polarity. So that means that each of those three fingers are the same polarity, and the same on the other side. So these margins don't actually contribute to the capacitance, but they need to be there so that you don't end up shorting in that region. So you don't want this layer of electrode to short circuit to the other polarity. Otherwise, you're not able to store any fields or any charge in that space because it's just a short circuit. So the margins here need to be as small as possible, but still be functional. And we haven't talked in great detail about field enhancements, but anytime you have a sharp point, anytime you have a contrast in dielectric constant in permittivity, there's going to be an enhancement in the electric field. And so a lot of times failure will occur at anytime you have these kind of edges and boundaries, because that's where the field is going to be concentrated. So those margins end up being very important because they're a region where a lot of the field is concentrated, but you want those regions also as small as possible to be able to maximize the energy that you can store. And then, of course, we want to do all of this with high permittivity materials in order to maximize the capacitance that we're after.
Jeff,
So this
I
is
have
what
a
we're going to.
question.
Yes.
For the layers, you're talking about like edge effects and how that really matters.
Mhm.
In between the gray layers and the gold layers, if you're like sintering two materials together, how rough can those surfaces be? Or will those like different angles of, yeah, or just how does surface roughness come into
Yes.
effect?
Great question. It matters. I can't give you an easy answer to it. It's great if it's below this certain value, and it's a problem if it's above this value because it depends on everything. But you're right to note that, yeah, I've oversimplified everything by drawing it all planar here. Of course, it's not planar. We'll see some more actual SEM images showing a little bit of roughness in this region. In this case, the SEM that I'm showing is actually multiple depositions from a solution perspective instead of from powder based, but you still see discrete different layers in there. And those are all within the dielectric. So the roughness of that surface between the electrode and the dielectric layer absolutely is an important parameter. The higher the roughness, the higher the surface area. The higher the area, the higher the capacitance, right? So in one level, you could think of that as being a good thing because it gives you more area. But because of the field enhancements that go along with those sharp points or just any curvature at all, that is going to limit the amount of voltage that you can apply before you get breakdown, before you get other sorts of field concentrations and additional leakage and that kind of stuff. So it doesn't actually have to break down and cause a lightning bolt within the material for a critical failure to be a problem. You could just have a little bit of extra roughness where you've got, so like if there's a nodule of the electrode that is pointing out, that means all of the field is going to be concentrated right there. It's going to be a leaky point. So you'll have a larger amount of leakage in that region. So often we do everything we can to minimize that surface roughness. But as you point out, and as we're going to get to in a little bit, trying to sinter two very dissimilar materials together at the same time, which is required if these are actually going to be scalable and commercializable and cheap, it's tricky. So yeah, we'll get into that in a little bit more, but great question. Did that help a little bit, Shannon?
Yeah, thanks.
Okay. All right, so we are going to try to do this impossible task of making large area, very thin layers, high permittivity material, and we're going to do it cheaply. So that's why I'm walking through this as an example for MLCCs, because it brings all of this together in a way that I think no matter what we're making, we can take some clues and hints and inspiration from different pieces of this. And just as a reminder, we use relative permittivity and often get lazy and call it dielectric constant, but it is not at all constant. And that's going to be an important continuing theme as we go through the rest of this. So how do we make these? I took this just cartoon schematic from Ming Jianpan's paper way back in the day that was introducing these just the concept of a multilayer ceramic capacitor to power electronics crowd. And so you start with a ceramic powder, mix it into a slurry, and tape cast it into a thin layer. So this is massively scalable. I won't say that it's simple necessarily because there's a lot that goes into it, but it is very mature. So there's a lot of industrial knowledge about how to start with ceramic powder and effectively tape cast well. And then so once you have this tape, so you can actually make a continuous tape. This will end up being something like 40 or 50 volume percent ceramic powder, about 40 or 50% binder by volume, and then a few other constituents thrown in, so dispersants and anti-foaming agents and lubricants and all of these different types of things. All of that you're going to have to get rid of. I mean, the ceramic powder is what you want, so you're going to have to go through a binder burnout, extended binder burnout in sintering state. So keep that in mind as we go through all this, is that we've still got 50% of our volume that we have to get rid of that was a binder. So that matters from both the process control perspective and the local partial pressure of oxygen perspective. We mentioned that in the last course a little bit. It is also really important from an environmental handling perspective. So if you're doing this tape casting process with water and aqueous-based additives, that's a lot less expensive to deal with hazardous waste and disposal and those kinds of things than if you're using organic solvents. However, a lot of times the organic solvents give you much better performance. They give better wetting characteristics and faster drying characteristics and less surface tension, so less stresses during the drying and lamination, all these kinds of things. So it's always a big balance between trying to develop a new binder system that's aqueous or non-aqueous, because they have different challenges there. Regardless of which approach you use, you end up making sheets out of this tape. So this tape still contains a lot of binder in it. And we'll screen print on electrodes. So if we think back to each one of those individual layers in the cartoon that I drew on the last screen, the gray electrodes were offset and stacked. That's just what we're printing here, as we're printing up each layer of that and then stacking them on top of one another. So they have to be aligned just right so that you get one layer here and the other layer there with maximum overlap, but not shorting. So then we'll go through a lamination step. So this lamination step is unbelievably underappreciated. So you start off with all of these, you heavily engineer the process to get the tape made in the first place. And now you've got discrete layers. You've put your electrode screen printed layers on top of it, and you're stacking it up. But you have to get all of these layers to stick together. And so that lamination process helps these layers stick together. One way to do that is to heat it up to where your part is just above the glass transition temperature of whatever your binder is, so that it's kind of gooey. And then you add a little bit of pressure. So a little bit of heat, a little bit of pressure helps to glue everything together so that it doesn't just turn back into potato chips and fall apart when you put it in the furnace. One trick that is often used here is to add just a little bit of the parent solvent between each of these layers to help those sort of fuse together. You use too much and you lose all of the nice clean lines from your screen printing. So you don't want to put too much of that solvent in there and make everything gooey, but you want to add just enough to assist with a little bit of interlayer diffusion, so that during this lamination step, you start with a bunch of discrete layers and you end up with one solid body that used to be layers and is now all coherent together. And you need that to be coherent, because the next step is to go through and dice it up. So when we're in this stage, it might be the size of a sheet of paper. It might be the size of, a floor, and just massive layers. Then we dice and cut it into the types of sizes that we're looking at for the final part. We're very close to them. So this is when we'll go from having a massive meters long, meter or more wide set of laminated sheets into the individual components that are going to be the ceramic capacitors that might be centimeters for some of the very large ones. They might be, tens to hundreds of microns for some of the really, really tiny ones. And then we throw it in the furnace, just like everything else we do in ceramic processing. There's a furnace step of some sort. So in this case, we're going to burn out the binder as slowly as necessary, because if we just throw it in and heat it up too quickly, then we convert all of that organic binder into CO2 very quickly and create a lot of gas pressure, and we just turn our very fancy multi-layer capacitor into a bunch of powder again, because it's all that binder burnout has basically exploded it. So we want to do this slowly. In order to help with that, a lot of times during this process, we'll end up using 2 or sometimes even 3 different binder systems. So you'll use different molecular weights. You use different chemistries that will have different burnout behaviors. So they'll have they'll be removed at different temperatures, so that when you come to this binder burnout stage, you can burn out a little bit of your binder, and that leaves porosity behind. That makes it easier for the rest of the binder to go away, and it doesn't all just leave all at once and create stresses and other problems. Then we have to sinter. So in this diagram, the binder burnout and sintering is just one simple step. You throw it in an oven and you're done. But as Shannon alluded to, think about what's actually happening in this case. We have an electrode layer of some sort. Let's say it's platinum, or it's silver, or it's nickel. It's a metallic layer of some sort. And then we've got our dielectric layers on top of it. And in each case, the ceramic dielectric layer started with 50%, roughly 50% solid powder and 50% binder. And the metal layer also started with something like 50% by volume metallic particles in some sort of a binder system. These are very different materials, and we want them to all sinter and densify at roughly the same temperature and time. They have to do this together. And we've already stacked up 5, 10, 1,000 layers of these, and they all have to sinter together, because if they're not sintering together cohesively, then for one, we might end up with stresses that everything falls apart. For another, we might end up with cracking. And cracks inside of this capacitor are going to be weak points for whenever we apply an electric field later on, and it's not going to function as a capacitor. It might bend and warp all over the place. So the sintering part is extremely difficult to optimize for each one of these. One helpful aspect of it, though, is that at least the metal layers that we're using, those, we want them to be as continuous as possible, because if there are any discontinuities in the metallic layer, then that will reduce the amount of capacitance that we'll get out of the part, and it will reduce the amount of energy that we charge that we can store within it. But having a discontinuous metallic layer is much less bad than having a discontinuous ceramic layer. So if we have a hole or a pore or a gap in the dielectric layer, that makes it way too easy for charge to flow through there and short circuit. And if you get a short circuit, then the material is dead, either because it just can't store charge at all, or if it stores a little bit and then short circuits and ends up creating damage, maybe you get a lightning bolt and zaps the entire device that it's sitting inside of. So if we're going to sacrifice the continuity of either of these layers, we want the metal to be a little bit less precious than the dielectric. The good news is that most of the metals that we're using are reasonably ductile, especially at the sintering temperatures, and especially compared to the ceramic layers. So they can accommodate some of the stress and strain of sintering a little bit better than the dielectric layers. So now we've sintered these materials, and right now they're just layers. I'm drawing the electrode layers only. Let's see, try it again. So let's say that we have these electrode layers that are drawn like this, and then in between, we've got all the ceramic. But now we have to actually be able to contact these to one another. And in order to do that, we do what is called termination. So we'll bring in basically a paint that we paint on the end. That's what this layer, this step is called. And so that just allows you to connect all of the every other layer, so all of the positive sides with all the negative sides, so that then when we plug this into our device, we don't have to connect every layer individually. We just touch the positive electrode and the negative electrode, and away we go. So that termination is often done with a tin containing metallic paste of some sort. So it's often the same generic or same general chemistry as the electrode metal. So whether that's silver or platinum or nickel or whatever, but then we'll also include some tin so that we can solder to that. So that including a little bit of tin in the termination helps with soldering down the road significantly. So we've gone through this termination firing step, and it's generally going to be at a significantly lower temperature than the binder, burnout, and sintering. And then we have to measure. Every single one of these is going to be measured to make sure that it works, because this is a complex process and there's a lot of stuff that could go wrong. So you've got to measure every single one of them to make sure that it's good, and then off they go. So that is a very hand-wavy description of what happens in the cartoon version of multi-layer ceramic capacitor fabrication. But just so you have an idea of what goes into the actual fabrication portion. Now let's get to what can we do to tweaking the chemistry in the unit cell and all the fun material properties themselves. But before I get to that, I just want to, again, this is kind of an ode to the MLCC celebration of the ceramic capacitor industry. I'm sure everyone has heard of Moore's Law. There's a lot less talk about it these days, and because of that, this plot is actually relatively old, but the concept is still valid. So what you see on here is that in blue, we see the number of transistors per chip, and in red, or sort of reddish brown, that's the clock speed of those chips. So the semiconductor industry, Moore's Law was all the rage forever, because the number of transistors per chip just kept doubling and kept doubling and kept doubling, and the chips themselves were getting, the transistors themselves were getting faster and faster and faster, and we ran into a power wall where we just couldn't get the power into and out of those chips fast enough. But the transistor scaling continued. So the number of chips, number of transistors per chip just kept going. Nobody ever talked about the fact that the multi-layer ceramic capacitor industry was keeping up with this, and in some cases even exceeding it over this entire range. So this is the Moore's Law was applied to the silicon semiconductor integrated circuit industry, and the multi-layer ceramic capacitor industry kept right up with them in terms of the number of layers per capacitor, the capacitance density per volume, all of that. Just unbelievable scaling that went right along with it. So up here in the top, I've got an example of 800 dielectric layers, each less than a micron, and this was in 2000. And that process has continued since then. So just to wrap your head around scale, on the left here, I've got grains of table salt with a micron scale bar. That's 2 scale for all of these capacitors. So I was using Murata earlier because they have the fancy marketing materials. Kyocera does the same thing. Tao Yuden does the same thing. TDK, all of these capacitor companies are making just spectacular gains in this area. So just think about the physical scale there. All right. So from that, we're able to cram a whole bunch of energy and a whole bunch of charge into a very, very small package. And that's why you're carrying around about 1,000 of these in your pocket in your cell phone right now. So it's just some examples here, is that when we look at the total packaged capacitor, and then we zoom in and look at the individual layers in between them, and then zoom in again, you see this is a metallic layer, so that's an electrode, this is an electrode, and then we've got the dielectric in between. And you can see get rid of the rest of this, you can see that the dielectric consists of many, many, many layers inside of there. And so the reason for that is that, as we'll get to later on, if you think back a little bit to the defect chemistry that we were talking about, if you have any charge defects at all, and you apply a field, they're going to move under that field. And so putting in grain boundaries in the way will slow down that mobility and increase reliability. So a general rule is at least 3, 10 is even better. Grain boundaries between the electrodes is a good target. At the same time, as we'll talk about in a little bit, you don't want the grains too small, because then you start to lose performance. So you'll notice that the electrode grains are much, much larger. And then part of that is because it doesn't matter as much. Part of it is because most of the electrodes that we're using are going to center at lower temperatures than the dielectrics. So the mobility is going to be higher. And so we just end up with bigger, fatter electrode grains. We don't want the electrode layer thickness to be too thick because that just takes up more volume that we could be using for energy storage. But you need the electrode layers to be thick enough that they can get the charge, the electrons in and out as fast as necessary. So the thicker the electrode layer, the higher the operating frequency can be. The thinner the electrode layer, the more capacitance you're able to get per volume. So it's a balance just like everything else. And so this top layer shows a packaged capacitor all the way down to the individual layer. This center row is showing just the example of the particles themselves. So in a centered capacitor, this example shows grains on the order of 200 nanometers. And now as the industry has progressed, they're operating with particles and powders on the order of 10 nanometers. So just continuing to shrink and shrink and shrink and shrink. So when we look at these, again, these are some old examples that are borrowed from Sakata-san from Murata. You can see in cross section here, the dark areas are the electrode layers, and the bright areas are the dielectric. And you'll notice, for example, here's a region where the dielectric actually sort of oozes through. The electrode layer is discontinuous and has gaps in it. But remember, this is we're only looking at a two-dimensional slice, and so this electrode here, if we extend into and out of the page in some way, it's still going to be connected to these other regions around. So it's going to be sort of like a Swiss cheese. It's got a hole in it. That hole is filled by the dielectric, but that's no big deal because as long as that's insulating, it's fine. We've lost a little bit of performance because of that, but it doesn't short circuit. If this were the other way around and it were the dielectric that we're shorting through, or sorry, and it were the electrode that we're shorting through the dielectric, then that would be a real problem because it wouldn't be able to operate at all. And so these are just showing a couple of examples way back from 2013 about comparing half micron to a third micron, so 350 nanometer layer thicknesses 12 years ago. So you can imagine where things are now as that scaling has continued. And again, just so that you can appreciate scale, Murata happens to be the largest. They sell about 20 billion MLCCs every single day. That is a massive, massive number. And each phone's got 1,000 of these, and they're way less than a penny a piece. It's impressive. So that's a bit more about the capacitors themselves. How do we make this actually work with the barium titanate material that goes into it? So I showed some version of this earlier when we were talking about crystal symmetry. And we were talking about, do we start with the perovskite structure, and it can have several different symmetries associated with that same basic crystal structure. So we've got cubic, the high temperature, tetragonal at lower temperatures, orthorhombic, and then rhombic equal below that. And at each one of these phase transitions from one of those symmetries to the next, we see an increase in permittivity, the largest of which happens between the tetragonal and cubic. So if we want a really high permittivity, then we probably want to be somewhere near one of these phase transitions. As I always like to say, the materials are just like people, that they perform the best when they're frustrated. This is the same kind of scenario. So if you have the material operating near a phase transition where it's a little bit confused about where it wants to be, where it's most stable, then you're going to get the highest performance out of it. However, you'll notice that these are changing by a factor of 5 in permittivity, even just on this scale. So you probably don't want the performance of your cell phone to change by a factor of 5 as you change temperature. So as you walk around go outside and it's cold, you walk into a heated room, and you don't want that to change so much. So how do we deal with that? Oh, also, this is along the axis, so that would be for example, this way. And this is the C-axis, and there's a massive difference in permittivity depending on the crystallography. So we want to maximize this as a whole, but do it in a way that that is stable with temperature and crystallography. So how do we go about that? This is one of the developments of the late 70s, early 80s, mid 80s, and then continuing to progress from there. Is that we can basically chemically modify the material so that at any point, some portion of each grain is going through this phase transition. And if we have a chemically heterogeneous grain structure, which I'll show an example on the next page, we're going to end up with a grain that has a chemical gradient across it. So that at one temperature, this region is undergoing this maximum permittivity. And then at a different temperature, the maximum permittivity is right there. So the phase transition is right there. And then we just come up with a gradient all the way across the sample so that some portion of it is always contributing this maximum amount. And then you average it out over the entire temperature range that you care about, and you can end up with a reasonably stable transition. And while I really like this plot from a conceptual perspective, it's kind of cheating by having that offset. So what you actually end up with is the overall average way down here. But it's the stability that's important rather than the actual maximum. So one thing that enabled this was a lot of foundational work looking at the effects of different alloying elements on the phase transitions within barium titanate. So I've put this classic plot on the right. This is the version that I took out of the Jaffe cookbook, showing the effects of different alloying elements. So if you replace barium with lead, then this temperature of the tetragonal to cubic phase transition goes up significantly. If you replace it with calcium, it doesn't change a heck of a lot. If you add strontium, then that phase transition decreases significantly. So this is the ROTC from low to high temperature, just like we saw on the last plot. And you'll notice if you look closely that if this is barium titanate AbO3, the alloying elements or the dopants that we're putting on the A site, so this is lead replacing barium, calcium replacing barium, strontium replacing barium, those cause shifts in these temperatures. If we look at the materials that are going on the B site, so that's these guys, the B site right there. So that's zirconium. We see that the result of B site doping tends to take these phase transitions and shift them toward or away from each other. And so generally doping the B site does what's called pinching. So it has the phase transition series compressed together or spread apart. Whereas generally replacing the A site with something else will cause the entire series to shift one direction or the other, and keeping the distances between those relatively similar. So what we end up doing is doping barium titanate with a gazillion different things, about a third of the periodic table, so that we end up with this chemical soup, so that we've highly optimized exactly what the heterogeneity, the intentionally heterogeneous sample, so that different regions are going through these phase transitions at different times to end up smearing out that phase transition series. And so these are largely to shift with the temperatures of each one of those transitions is happening. Zirconium in particular pinches the phase transitions together. Dysprosium, holmium, yttrium, magnesium, because magnesium is small enough that it actually goes on the B site largely instead of the A site, even though it's an alkaline earth. So these, and manganese, are all there to adjust the defect chemistry. So this is, you're putting a 3+ onto a 4+ site, which is an acceptor dopant. So that's to help mitigate oxygen vacancies if you need to sinter in a low PO2 atmosphere, for example. So if you are making expensive enough capacitors that you can use platinum electrodes and people will buy them, then great. If you want to make them cheaper, you're probably going to have to use nickel electrodes or copper. And nickel and copper require lower partial pressure of oxygen, so they don't oxidize, but that leads to increased oxygen vacancies in the barium titanate, so you can compensate for that with some of these. There's also multiple other aspects of it. So for example, manganese. Manganese is considered a magic dopant by many people in the industry because it's got 7 different valence states, and it is perfectly happy compensating for whatever other defects happen to be around. So just sprinkle in a little bit of manganese and your resistivity will go up in barium titanate. It does wonders. The other fun thing about the different lanthanides is that they're all 3+ for the most part, but they have gradually changing ionic radii. So on the lanthanum side of the lanthanide series, those species are large enough that they can actually substitute on the A site of barium titanate. At the smaller end, so ytterbium and lutetium and the smaller lanthanides, much prefer to go on the B site because they're small enough, they fit better there. So you can either have a 3+ on a 2+, which is a donor dopant up here, or you can have a 3+ on a 4+ site, which is an acceptor dopant down here. And so holmium and dysprosium happen to be right about in the middle. And so they can, they're just as happy being in the A site or the B site. And so they can end up being self-compensating. So if your sample needs, it's got too many oxygen vacancies and it needs to compensate for that, then maybe the holmium and dysprosium will hang out on the B site. If you've gotten your A site ratios just a little bit off, A site to B site ratios just a little bit off, these kinds of dopants can help compensate that a little bit. So that's one of the thought processes that go into doping and alloying these barium titanate based materials for capacitors. And so I promised the image of the chemically heterogeneous core shell structure. So this is a classic image from one of Clyde's papers showing the outside, the shell of this single grain. So this is a single grain of X7R barium titanate. So we still call it barium titanate, even though it's got 9 different elements or 12 different elements in it, or something like that. The outside is doped such that at room temperature where this image was taken, that material is cubic. So it's actually the transition temperature between tetragonal and cubic is low enough that this shell region is in its high temperature cubic form, even at room temperature. The inner core is in its tetragonal form, and you can tell that from the twinning. So those are domains that we're able to see there. They're essentially martensitic twins that form when you cool it down from the cubic phase to the tetragonal phase, and you form these twin structures. Into the domains and domain walls a bit later today or tomorrow or next week. So what we can see with this is we take this core shell structure, we know that boundary right between those is going to be right at the peak in relative permittivity. So that's the highest permittivity region is right where that boundary is. If we take this sample and heat it up, we will see the core gradually shrink as more and more of the grain becomes cubic. And as we cool it down, we'll get more and more of that core growing as a larger volume of the material is below its phase transition temperature. So the sketched cartoon version of it is shown here, where they're claiming it's pure barium titanate surrounded by a highly doped region. The first version of this really was you start with pure barium titanate and then put in stuff at the grain boundaries that will diffuse in so that you get a gradient in doping concentration. And this is what's shown here, where they're using bismuth and tantalum as the dopants that would help form this core shell structure. That was just the first generation sort of proof of concept. People have moved well beyond that just simple doping at the grain boundaries perspective, but the concept sticks around. You notice something else on here that says fast firing. In order for this to work, you need to balance the diffusion coefficients and the diffusion rates of all these different dopants so that you don't sinter long enough that everything becomes homogeneous, but you do sinter long enough that everything becomes dense. And so it's a race between getting the dopant materials to diffuse where you want them, and the densification to happen without everything being completely homogeneous and losing the advantages of the core shell structure. So this is one of the early stages of going to a fast firing sort of approach. So that doesn't mean you just throw it directly in the furnace after you did the tape casting, because then all the binder combusts at once and everything goes away. You have to do the binder burnout and then gradually transition it over to as rapid a firing as possible. And in fact, I think I've got a slide later on showing some of the examples of this, but this can control not just the diffusion and sintering of the dielectric layer itself, but massively affects the continuity of the electrodes themselves. So the electrodes, the longer they're hanging out at high temperatures, the more they're going to de-wet and pull away and increase the roughness, as Shannon asked about earlier on, and then decrease continuity, which is going to gradually reduce the amount of effective area that you have. So one of my favorite couple of papers, Anton Polotai and Clive published maybe a decade or so ago, just a couple of papers in the Journal of the American Ceramic Society that essentially overnight, every large-scale capacitor company in the world went from the standard relatively slow kiln processing that they've been using to rapid firing of their MLCCs because of what Anton and Clive had shown in these papers, the advantages of a very rapid sintering step for MLCCs. So, great question, Yang. So I'm assuming that you're talking about the phase transition associated with this transition from cubic to tetragonal. So we'll get into that a little bit more, but for right now, I'll just point out that this for barium titanate, so pure barium titanate, without any of these dopants, the stress associated with that is so that the lattice parameters are roughly 1% different. So if you go from cubic to tetragonal, it's about 1% strain between the A and C dimensions, which is not nothing. 1% strain is a lot for a ceramic, but it's relatively easily accommodated by forming these twin structures. And so for barium titanate, that amount of strain associated with that phase transition is usually not enough to lead to cracking. You can accommodate it by just forming these twins. For lead titanate, pure lead titanate, that strain is about 6%. And so lead titanate absolutely will crack and fracture when it goes through that, or it can, when it goes through that phase transition. Barium titanate is not so bad. So that's one of the reasons that we use that barium titanate is so useful, is that we're able to get away with the domains that form accommodating that strain. So hopefully that helped. All right. So another challenge associated with this, we spent the first 10 slides of this discussion talking about how we want the grains to be as small as possible. We want the layers to be as fine as possible. Well, it turns out that in barium titanate, this is for pure barium titanate, so not the X7R version, but there's a very large grain size dependence on permittivity. So if you look at very large grains, so 50 microns, as you decrease grain size, you see a large increase in the dielectric constant, relative permittivity, at all the temperatures below the cubic to tetragonal phase transition. So the Curie point. So the Curie point is this phase transition between cubic and tetragonal. And so the largest difference is seen for that tetragonal phase, but we still see an increase in permittivity for the other lower temperature transitions as well. So that's encouraging. That means that as we get smaller and smaller grains, that we're going to have even better relative permittivity. That's exactly what we're looking for. This was Arlt's paper in late 70s, early 80s. Matt Fry and David Payne came along and said, well, what happens if we go even smaller than 1 micron? And Matt showed that as you get below 1 micron, those gains just plummet. So especially right at the phase transition temperature, you lose a lot of the maximum in relative permittivity that you see around a micron as you get smaller and smaller and smaller and smaller. So these are still very large relative permittivities compared to titania, which is about 100, or compared to alumina, which is like 10. but they're nowhere near the 10,000 that we would like to get if we want to maximize the relative permittivity, maximize the capacitance in these materials. So this was a big concern. So Matt spent his entire thesis trying to understand how and why this happened. And it turns out that it's a combination of the grain boundaries themselves are not as high permittivity, so they are disordered, and you don't get the as strong of a response to an electric field in those materials at the grain boundary. And the domain structure that we saw on the last page, where we had those twin structures, because the boundary between those, I mentioned that's basically the material is very frustrated. The boundaries themselves end up giving you a significant increase in the relative permittivity because they're sitting there sort of cubic-ish, and so they're analogous to sitting right at this phase transition between tetragonal and cubic. So the larger the grain, larger the domain boundary volume you have, the larger the permittivity. The larger the grain boundary volume you have, the lower the permittivity. So the difference is domains are cohesive and coherent structural boundaries. So you still have the same lattice, baseline lattice across a domain boundary. At a grain boundary is all sorts of disordered, and that's why the grain boundary is low permittivity. Domain boundaries are high permittivity. And we'll get into domains themselves a bit later in more detail about ferroelectrics. But the point is for this is that, yes, we get an increase in permittivity as we reduce the grain size from ginormous down to around a micron. But once we get below a micron, then the relative permittivity starts to drop. And that's essentially because within these really small grains, you end up, each grain is only one domain. And so you lose the advantage of having, in a larger material, you can have multiple domains, and then you get the increased permittivity of having that domain boundary in there that can sort of wiggle back and forth as you apply the electric field. So think about that. We are trying to make these materials as high permittivity as possible, and we need a thin layer, and we need that thin layer to have multiple different grains in it. So if we want multiple grains, if within 100 nanometers of a layer, each grain is going to be 10 to 20 nanometers. And the whole reason we're using barium titanate is because of this very, very high relative permittivity. But as we make those grains finer and finer and finer to be able to fit into this 100 nanometer thick layer, the permittivity of each of those grains is now decreasing. So we have to fight harder and harder along the way. In addition to that, as we apply an electric field, so this is applied electric field, the relative permittivity drops. So this is commercial barium titanate capacitors. As you apply a field, the relative permittivity drops. And so one way to think about that is if you've got these springs that we talked about before, if we pre-stretch that spring by applying a DC field, the amount of additional permittivity that we get by having an AC wiggle on top of it is smaller and smaller and smaller. And so what that really means is that now we've got a grain size effect to deal with, plus as we get thinner, the same voltage leads to a higher electric field. A higher electric field leads to a lower permittivity. So everything we're doing to scale things and make the physical size smaller is actually making the performance worse. But we need both. And on top of that, as I mentioned before, we also need to do this with cheap enough electrodes that we can sell these things. So we talked about defect chemistry a lot earlier this week. If we're going to sinter on top of or using nickel electrodes, co-sinter with nickel electrodes, we have to do this at a very low partial pressure of oxygen to avoid oxidizing the nickel. Because if you have a nickel oxide electrode, it's not conductive enough to be an electrode. So we have to keep the nickel metallic, and we have to keep the barium titanate oxidized, which is another reason that we throw in a lot of these acceptor dopants, the lanthanides and manganese as well. Because if we end up forming titanium 3+ species, so you end up with titanium 4+ next to a titanium 3+, you can actually get electrons hopping between the two. And that leads to what's called polaron conduction. So it's essentially electrons hopping from one species to the next, and this can happen when they are nearby one another, and it's a species that can change valence, and that just leads to another leakage pathway. So you've got that capacitor with a resistor in parallel with it, and you just reduce the amount of resistance of that parallel resistor. So now you're able to leak more current through it, which is not at all what you're after. So we try to avoid low partial pressure of oxygen because that can cause problems with titania and can cause problems with oxygen vacancies. But we need to operate at low PO2, or we need to sinter at low PO2 to keep the nickel reduced as nickel metal. So that's a whole other challenge. But it's one that's largely been tackled successfully. Even more impressive, and I want to use this as a transition to some of the actuator and piezoelectric applications that we're going to get to. People have now begun co-firing a lot of these multilayer structures with copper. And so copper is essentially the same as nickel, very similar to nickel in terms of its challenges, but requires an even lower sintering temperature. So now we have to do all the stuff that we're doing with nickel. We can have just a little bit higher oxygen partial pressure, but now we've got to knock off 200 degrees C from the sintering temperature because otherwise copper will melt. And so the fact that people have been able to make these multi-layer actuators for piezoelectrics with copper electrodes using the same kinds of technology and tricks that have been developed for the MLCC industry, I think is tremendously exciting. So we're going to get into why this ends up being valuable from a piezoelectric application perspective in a little bit. The short answer is that if you've got a single layer and you apply a voltage across it, the amount of strain that you get. So piezoelectricity is apply a voltage, apply a field, and get a strain. The amount of strain that you get from that is directly related to the amount of voltage you applied. Well, what if I want the same amount of strain but at a lower voltage? I can do that by making these multi-layer structures so that the field that's applied can be the same because it's across a thinner layer. So each layer gives me the same piecemeal response, but now I can add that up in series, and so I end up with the same amount of strain as I got with that one, but at a lower overall voltage because I split that voltage across a bunch of thinner layers to give me the same field. Now, this version is going to require higher current to operate, but in many cases that's perfectly acceptable. So I just wanted to use this as an example to show that everything that we just talked about from a multi-layer ceramic capacitor perspective is very much applicable, even if you're not actually interested in trying to compete with the capacitor manufacturers and make MLCCs. A lot of the tools of the trade and tricks that they've developed, we can apply to a bunch of other materials and devices as well. And it's the amazing thing is the scalability. So scalability in terms of thickness, so being able to reduce thickness to take advantage of lower voltages, lower thicknesses, higher effective fields, those kinds of things, as well as the commercializable scalability. So the fact that once you get this process down, you can crank out tens, hundreds, billions of parts any given day instead of making them ones and twos. So any questions very broadly on MLCC behavior and fabrication? So another example of a sort of parallel industry that has been able to take advantage of a lot of the capabilities developed by the MLCC industry are LTCC and to a little bit lesser extent HTCC. So you're probably familiar with some sort of a printed circuit board. So if you've ever taken apart your phone or your old Nintendo when you were growing up or whatever it was, you saw some sort of a yellow, green, polymer fiberglass based circuit boards that had a bunch of discrete components wired into it. So those are great. Those are cheap. They are everywhere. But in many cases, what you need is something that has similar sort of capabilities, but maybe it needs to be able to operate at a higher temperature. Maybe it needs to be a little bit more mechanically robust. Maybe it needs to be more chemically robust. So for all the reasons that we use ceramics for anything, these ceramic packaging in carrier types of technologies end up being really important. So the reason I loop this in with the MLCC capability is because a lot of these layering and tape casting, lamination, and alignment sorts of techniques are used just for all over again for LTCC. So the vast majority of these, the carrier, the LTCC component is called low temperature. It still requires sintering at 750 degrees C. So it's not super low, but that's low compared to what it would be for pure alumina. So these are generally alumina based, and they have been engineered with some liquid phase glass additives so that we can sinter these things at reasonably low temperatures. So 750-ish. Sometimes I guess the early ones were 900. Some of them have come down since then. The classics are still centered around 900. But from that, you can actually bury silver conductors inside of these. Some of them have been extended to copper and nickel and a bunch of other metals as well. The point is that we can take the same kinds of tape casting, stacking, lamination, cartoon that I walked through for MLCCs, and now do this with other materials and get drastically new capabilities that are integrated into a final component that's co-fired, and then on top of that co-fired block, we can then bond in, solder in whatever other components that we want. So the computer chip, integrated circuit, discrete capacitors, like we were just talking about, MLCCs, inductors, whatever else we need. And so the real advantage here is the flexibility that comes along with that. So once we've got a platform based out of this LTCC system, then you can build all sorts of good stuff. It's not just limited to the electronic components. It's not just limited to electrical devices. So there's an entire subset of the industry that's built around making microfluidics out of this LTCC capability. And it all comes out of the same kinds of techniques that are used for MLCC that we just described. And so now you've got massive variety of function that you can get baked into literally baked in, because it's co-centric, into this robust package that's alumina with whatever else embedded in it. So you have metallization, you can have 4 channels, you can have all sorts of good stuff. So these are just some examples. HTCC in general, same kind of techniques, but less liquid phase and therefore higher sintering temperature. And so you can't get away with using aluminum or silver wiring. A lot of times it's embedded metallization. It will be platinum or potentially nickel, other types of higher temperature metals. But the HTCCs will therefore have properties that are a little bit closer to raw alumina. So higher elastic modulus, higher operating temperatures, higher hardness, stiffness, all that kind of fun stuff. So those are just some examples. And to wrap up today's, I'm unfortunately going to have to skip out just a couple of minutes early, but I don't want to jump into too much on the ferroelectric stuff before we get too much further. So I'm going to wrap it up here. And the thought homework for today is to think about what we just talked about in terms of scaling. Geometric scaling, making things thinner, economic scaling in terms of cranking out more parts for lower cost. How might you be able to apply some of those ideas to whatever it is you're working on? Again, you don't have to send this to me in an email, but you're welcome to if that helps give you the incentive to do it. If there are any questions, please let me know. And I look forward to jumping into a lot more detail about ferroelectricity and piezoelectricity next week. Take care, everyone.